Hydrogen is an exceptionally efficient and versatile energy source, but its potential to power a clean economy is entirely undercut by how we currently make it. Right now, 96% of global hydrogen production relies on fossil fuels. That breakdown is 48% natural gas, 30% petroleum, and 18% coal, leaving just a 4% sliver for clean production. Extracting hydrogen from these sources requires thermal cracking and reforming processes. These methods strip out the hydrogen, but they also release massive volumes of carbon dioxide, nitrogen oxides, and sulfur oxides directly into the atmosphere. As long as we rely on carbon-intensive extraction, meeting global net zero climate targets is a mathematical and biological impossibility. We have to completely overhaul our production methods. This diagram shows the mechanics of water electrolysis. Using direct current, these four primary methods, alkaline, PEM, AEM, and SOEC, split water molecules free of greenhouse gas emissions. As the chemical reaction separates the water, it yields hydrogen at up to 99.99% purity. However, this process carries a fatal economic flaw. The massive electrical energy required and the steep capital equipment costs make electrolyzed hydrogen up to 3 times more expensive than steam methane reforming. Those high capital costs are driven primarily by the hardware itself. The electrodes in these systems rely heavily on rare, highly expensive precious metal catalysts, like platinum and ruthenium, to maintain the reaction. Flawless chemical purity is commercially useless if the economics cannot scale to industrial levels. This schematic illustrates biomass gasification. Feeding agricultural waste downward into a reactor creates a carbon-neutral energy cycle. But raw biomass has low energy density. Conversion efficiency remains limited. The process also introduces a severe mechanical threat. Thermal conversion inevitably produces biomass tar, a highly viscous, corrosive liquid byproduct that blocks and destroys pipelines. Biomass solves the carbon emission equation perfectly, but its corrosive byproducts introduce costly hardware vulnerabilities that make widespread adoption difficult. This brings us to chemical looping gasification. As detailed in this flow cycle, the system uses metal oxide oxygen carriers to react with biomass and steam. This naturally separates pure hydrogen within the system, eliminating the need for expensive, energy-intensive gas separation plants. But these carriers suffer from sintering. Under extreme temperatures, the crystalline structure of the metal oxide melts and collapses, completely losing its reactive surface area. The massive financial savings gained by avoiding external gas separation are entirely offset by the rapid, inevitable degradation of these carrier materials. Looking at these 3 primary clean technologies side by side reveals a strict pattern. Electrolysis is blocked by a massive cost barrier, biomass is compromised by tar byproducts, and chemical looping fails due to material degradation. Every alternative is trapped by a specific material science limitation. The strategic imperative for the industry is clear. Future investments must pivot away from proving basic feasibility. Research and development needs to focus exclusively on engineering cheaper non-precious metal catalysts and highly durable oxygen carriers. Clean hydrogen is technologically viable right now, but until these specific material breakthroughs drive down commercial costs, fossil fuels will continue to hold their 96% dominance over global production.